So what we're going to do is I will talk a little bit about development workflows, how you can use Julia, and then we will also take a look at how to use an HPC system environment. As explained, this is a course about HPC with Julia or Julia for HPC. Therefore, it's also nice to know how to actually run Julia on a large system to utilize all of the computing power of such a large system. So one way would be the old school thing. You have a text editor and a terminal, and you just write your code, and then you run it. So this is more like a traditional thing. You have your C code, you compile it, you run it. So it's quite simple. There's not much complexity in it. You just need an editor and a terminal, another shell, and you can choose whatever editor you like, but there's not much of an interactivity. And every time that you run Julia, it again needs to load Julia, needs to load all of the packages, and then execute it. And then we also have one nice package. So you can use the REPL, and with the REPL, you read and then execute and the expressions that you entered into the prompt of Julia, and then it gets executed and prints the result, and then you get back, and you have an implicit global variable environment. And there's a nice package called revise.jl, and this allows to combine the REPL with entering your code into a normal Julia file. So therefore you can have your editor, can type it, and if you're using revise, then you can add the script, and revise will reload the code once you modify your input files. And this way you can combine this and have a normal editor where you can edit your code and then run it in the REPL. Another possibility is to have a full-fledged interactive development environment, for example, VS Code, and VS Code has a Julia extension. So I think there was also like a more specialized Julia environment, but I think it was discontinued in favor of the VS Code Julia extension. And this gives you then all of the features that you know from VS Code, and also integrates Julia with autocompletion, and you also have a REPL, and it shows the plots that you generate, and then you can then also have some nice hotkeys to control Julia from your IDE. Now, for myself, I'm more on the old school thing where I just write Julia and then run it. But there are many possibilities, and this is also kind of comfortable to use Julia in a more interactive way. Next thing are dependencies in package environments. So this is a large problem for every kind of language. You will go into dependency hell quite quickly. And here Julia comes with its own package manager and simplifies your package management drastically. Yes, please. Yes, yes, exactly. Thanks for mentioning. What you can do is you can, if you need a dependency, a package, you can switch your REPL into the package manager mode with this closed bracket, and then you can define in which packages you want to add. They will be installed. You can remove them and then instantiate them to download and recompile them. You can look at the status of which packages are added and used right now. However, if you want to guarantee that your code is always compatible, you need to take care of or think about the version of your dependencies. So there could be a version change, and then your code won't be compatible anymore. So this is the typical problem if you're using many packages and have a lot of dependencies. And here has Julia offers these package environments. Now the idea is that you have these two files, project.toml and manifest.toml, that define inside of your folder, inside of your project, which packages are used for your project. If you activate this project environment and then add some packages, it will note which package with which version is used for this project. This way, you will always have well-defined dependency specification for your project. So you always know exactly which version you used. And using these two files, you can recreate your project environment. In Julia, if you have your project and you have these two files and your Julia code in your project, then you might wonder where are the packages that I'm installing. They are then installed in the Julia depot path. So this is a path in your home folder where all of the packages are installed. And this has a nice advantage, which is you can have multiple projects with multiple project environments. And if you have the same dependencies, then they are added only once to your depot. So they are only stored once, downloaded once in your home folder, and then all of the different project folders where you then activate your project environment, they can use then the packages that are stored in this one position. And for a specific machine, Julia can even store this compiled version of the packages. You will see when you install with newer Julia version some packages, it will go into pre-compilation. Therefore, the packages can define what kind of code should be pre-compiled because it's often used. And then this is not done when you are using the package, but it's done at installation time. And then it will just need to load the files from your depot, the precompiled versions, and then this speeds up the whole package using at the using time. The usage of your packages.
Get out of the package.
Escape. I think is it backspace? Backspace. Exactly. Now, as explained, Julia has a nice ecosystem of packages that is managed in a central place by the Julia project. So if you create a new Julia package, you can register your package with this central place. And then Julia, if you have used the package manager, there's a central place where it looks for packages and updates. So this package place is called Yggdrasil, like from the mythology derived. And here the community stores the packages and manages them. So this goes more into if you create your own package, what you have to do. There are then tools for building the binary packages and so on to add them to the Yggdrasil package system. Now we've already seen the JupyterHub, so I don't think that I need to repeat it. Or do you have any questions about the JupyterHub and the Julia usage? The so maybe one hint is that we tuned a little bit our JupyterHub, so it will be more comfortable for this course. For example, we used, so in Julia, you have this depot with the precompiled packages, and we actually created one depot that is used by all of your accounts on the cluster. So you don't have to install and precompile the packages yourself. And this is also nice. Julia then supports multiple depot paths. So this one depot path is just one of this one central in the list, and your personal one that is stored in the home folder of the account is then a different one. So Julia can look up if the precompiled version is already in one of the depots and then use that. So if you're using Julia locally on a different setup, then you will see that it always you have to add the packages and precompile them. Else, the JupyterHub is a nice way to do some interactive development with Julia on the cluster. But usually the cluster is used in a non-interactive way. Therefore, you specify the code, the jobs that you want to be executed, and then they're executed. For local installation, so this we also have some instructions in the repository if you need them. And there's also, I think, this new Julia app installer that's even more simplifies installing Julia on the system. It's not mentioned there, but you can find it on the Julia website. What we now want to do is we want to explain a little bit how to run Julia on an HPC system and how this works in general. Now here you see a very abstract schema of a compute cluster. And we will start from the right. And here on the right, we see the compute nodes. So you've already seen a picture of the cluster. I think here is another one. So it's basically just multiple racks. And inside of the racks, we have the compute machines. These are just servers. And each server is here a little box. And this is where your program will be executed on the cluster. And you can run your program on multiple nodes or run multiple jobs in parallel and so on. However, usually you can't just go to one compute node and then run Julia there. In a non-interactive way, you have to use this workload manager, the scheduler. And the scheduler makes sure that on the cluster where you have a lot of users using the cluster at the same time, it makes sure that there is no overlap or conflict of the resources. Therefore, you have to specify what should be executed, how long and how many resources you need. This means how many CPUs or CPU cores you need, you want to allocate, and you tell the scheduler what to run, and then the scheduler makes sure that it creates a schedule when it will be executed on what compute node. And to talk to the scheduler, usually you get a terminal, a shell on the front-end nodes. You connect them via SSH, therefore a text mode access. And then you can prepare your job, specify your job script, and then talk to the scheduler to say, okay, this is what I want to have executed, and the scheduler will make sure of the execution. And when it's done, you will see the results in your in the folder where you started it. It will create some log files, and you can write your result values into an output file. This is the usual concept of how to use HPC cluster. And for the connection, usually you use the VPN on our system. And in our case, we also have a training machine. If you want to use SSH, you can SSH with your credentials to the training machine and then jump to the jump host in the front-end nodes. Yes, please. This is just another node where you have to SSH into, and you have to SSH into there. This is just for our courses, so you don't have to use a VPN. So it's just called training. Therefore, I called it the training machine. In our case, there are so many tabs. Okay. If you have the JupyterHub, you can also just get shell via this terminal here in the JupyterHub. And then you can do the work also here. So, but you are here on the compute node.
Yeah.
Oh, I'm sorry. Really? Here, in the JupyterHub, you can just open here a terminal, and then you also have a shell. This is, in our case, a compute node, because when you started with the preset, it already running on one of the compute nodes. But in our case, that's fine. You can use it like this. But usually you go via SSH, therefore over with the terminal with the text mode, and access then using your credentials, using SSH, jumping to the training machine, and then you jump to this jump host, and then to you say SSH Nocta 2, and then you get a shell on the front-end node. So it's a little bit complicated, but then you will finally be there on the front-end node to access your data, prepare your jobs, and talk to the scheduler. Another thing in HPC clusters is, because this is about high performance, we have multiple storage systems, and they are mounted transparently to every machine on the cluster, therefore the login nodes and the compute nodes. And there you have your home folder. And if you get account on our system, it's always in the context of a compute project. And therefore, in this project, you also have a project folder. And these are stored and backuped on one storage. However, the access is not that fast to the compute nodes. And therefore, we have a different parallel file system, which is connected directly to this very fast network. And here, it is not backupped, but there you can store your input files and output files. And these are more directly connected to the compute nodes. So this is usually faster and more performant. So this is another thing that that's a point in HPC clusters.
Try to execute a job via Scratch, and your data is located, or the data that you need to access for this job is located on the project folder. Will this slow it down, or should I copy the data from the project folder into Scratch before executing a job to run it properly?
So the question was where to store the project data for compute jobs. The answer is somewhat complicated. It's also a little bit different for other clusters. So the generic answer is the data that you're using for your compute job should be stored in the parallel file system, because it's then connected to via this very fast network to all of the compute nodes, and then it should handle well higher loads. If you run a lot of compute jobs and then they access all the storage via the network file system, then this should be faster. Therefore, you work here, and then when you have some meaningful results that you want to save, in case of a meteor or something, then you can copy them to this data. Or you can also maybe store some code here that is used. So this folder is mounted read-only on compute nodes. So you can only write to your home folder or to the parallel file system in your compute jobs anyway. But you can read from the group folder here. And this is your an account-specific folder. This is a group-specific folder, and on the PFS you also have a group-specific folder. And if you want to know the complete truth, with the unpleasant details, it is that the PFS is optimized for large files that you don't have that many of. So if you have very many very small files, and then it can become slow in the case where the complete system is under load. So a lot of users are using the parallel file system. There's a lot of load, and then single accesses slow down. And in this case, it would be faster it can be faster to store them, for example, in the group folder. So usually it works fine, but then some user is doing 5,000 jobs that are very heavy on the I/O, on the access storage, and then suddenly your Python program that loads 10,000 files at the beginning, then takes not 30 seconds, but takes 10 minutes to just start the Python thing. It's yeah. But in general, this should be this is the generic answer to store your input files here. So for example, our Julia depot with the precompiled files, there are also like 30,000 files. I also stored them here just in case that some user will do something in our during our course here that will slow everything down. But this is specific to our system, but maybe it can be similar on different systems. Now I've already talked about compute jobs. So what are compute jobs? A job is basically a sequence of commands. It's like a shell script where you say, okay, now start Julia with these and these parameters, and then it will be executed. And in combination with the required resources. So how the wall time, how long should my job run? how many CPU cores do I want to allocate for my job? How much memory do I need? Do I need maybe some GPUs? And in some special cases, some software license things. And what you usually do in a non-interactive job, you specify a job script. And this is very convenient because you can, it's like just a bash file. Therefore, a text file. In the beginning, it has some magic line that says I can be executed. And then you have the parameters with the for the allocation, and then just some lines of what should be done. And then you pass this to the scheduler, and the scheduler reads it, sees, okay, you want 4 nodes for 10 minutes, and then it will look into its schedule. And we are using the Slurm scheduler system on our systems. Now, as explained, you can say I want a complete node in exclusive mode. Then you will get a complete machine, and the machine has 128 cores in the case of our Noctua 2 system. But you can also specify I just need 10 cores, and then you will your job will be executed on one node, and you can only use 10 cores, CPU cores. And then there could be a different job also at the same time running and on the shared node from a different user, or even your own job could run on the same node. And there's another special case where you, for example, allocate 10 cores of the 128 cores on the node, but you allocate 90% of the memory. Well, other users wouldn't have much fun with only 10% memory and the rest of the cores on the system. Therefore, if you allocate proportionally more memory on the node than CPU cores, then this memory allocation will be also transformed into core allocations in the billing, therefore in your contingent of your project. So you only get the 10 cores, but it from your account will be removed the resources as if there will be more cores allocated because you took so much memory. Now you can specify the exclusive parameter to Slurm, and then you get complete nodes. And if you don't do it, then you can specify how many cores you want to use. So reasons to use the complete node is if you want to, for example, use profiling or benchmarking of your code, then other code running from other jobs could interfere with your benchmark because you want to have your benchmarks comparable, and then this wouldn't be comparable anymore.
Then you Slurm just launch your script or whatever. How does the system manage that?
So the question is, if you don't use Slurm and you just run your script, so if you don't use Slurm, you run your script somewhere on one of these other nodes, and then the administrator will see it, and then they will kill your processes and will send you an angry email. Because these nodes are there to prepare your jobs, to transfer some data, maybe do some very light compilation, but these are not for heavy computation because these are also shared by the users. There are many users on these nodes, and they all want to just prepare their jobs. So if you would then do your heavy computational job, this will disturb the other users, and therefore your computation should be done on the compute jobs. And there are some default names for the output files, the log of your job, but you can also rename them. There are some parameters to give them a specific name or send the data to def null, and then it's to not store it. So here are some specific parameters. You can give your job a name. So this would be nice in your job list to see, okay, this was this specific job, my job, compute pi, or a specific simulation or something. So you can see it easier in your job list. Then the time that you want to run at maximum. If your job reaches your time limit, then it will be aborted with an out of with a timing error. So there is some. So you need to do some estimation how long your job will run. If you say it's too long, then the scheduler will have a hard time to find a good schedule to fit your job, because there are some other jobs running. And if you say, okay, this is my 4-week job, where should it be? When should it start? Then it's harder to find a spot, even if your job just runs 10 minutes and not 4 weeks. But you also don't want it to be aborted. Therefore, you need to do some estimation, then a little bit more of time. And then your account. Therefore, you get, if you have a project, you know the short string for your account name. Then how many nodes you want to allocate, and the partition. And we have multiple different nodes. They are disjuncted in the partition. And here we see the partitions. We have the normal partitions with the normal memory sizes. We have the large mem partitions with up to 1 terabyte of main memory. We have the huge mem partition with nodes with even more memory and some SSD storage. Then we have the GPU partition with the GPU nodes and the FPGA partition with the FPGA nodes. Yes, please. So usually you have a big project. You need to do a lot of computations. And let's say you have a simulation and you simulate some very important physics stuff, and the simulated time is, I don't know, 1 minute. And you're simulating a certain number of molecules. Then you can go back and see how long would it take if I'm only simulating 5 molecules, and the simulated time is only a few seconds and not 1 minute. Then you can just try it out and say, okay, I'm creating a job with this little one that takes, bless you, it takes maybe a day or half a day or a few hours, and then see will it abort it or not, and we'll see how long it will run. And then you can do a scaling analysis. How long will it take if I'm not simulating 5 molecules but 10 or 20 molecules? And usually if you have a simulation and it takes longer, then you can then check if I'm simulating 2 seconds, 5 seconds, and so on, and see if it scales linearly with the simulated time. This also may be different depending on your simulation. Therefore, you start with a small job and then check how long it takes, and then you can do an estimation of how long it will take if I do the complete computation. And what you can also do is you can implement restore points. Therefore, maybe every hour, your simulation program will just store the current state of the simulation into a file, and then it runs and gets aborted. Then you can continue the simulation with your restore point. This would also be a possibility.
Basically 2 days of computation will do something
or checkpointing. Like that.
Well, but then this is not. Is this a Slurm thing?
Yeah.
Really? Okay. So I was just talking about the generic concept of checkpoints or restore points, whatever you want to call them, in some simulation, some computation where you then store a specific state that you can then load later to continue. And I mean, this is quite application specific. I think there are some works that try to freeze your process, then store the complete memory and all the stuff, and then so you can later revive it and then let it continue. But usually this is implemented in your specific application.
The problems that most of the users asking us. First thing is that you mentioned that start from small, and see how much time it takes. Then you estimate how long it will take if I use certain number of nodes or cores. Also, on top of that, I would also set at least 20% extra time so that we don't take the 100% of time, and just because of 1 second, we can resolve this. Also, nice to have that.
Yes, exactly, like estimation and then some extra time. As said, there could also be slowdowns because of, I mean, if you have the complete node, then whatever happens on the node, it's your node, and then it's only influenced by computation. But if you're doing I/O on the storage, it goes on the network, and then this is like a shared resource, because then also other users can use the storage, the network storage, and so on. And then suddenly your job slows down because of what is happening on other nodes. So the computation is just as fast, but the I/O becomes slow, and then this can also then prolong your job theoretically. Yeah, you also. Okay. Now this is on the top you see the sbatch command, and the sbatch command is the command that you can give such an sbatch script. So you can pass the parameters on the command line. You say sbatch and then the parameters, and then pass the name of the script, and just have the commands here. Or you can combine it and put these parameters inside of your job script. And this makes it quite convenient, so you don't have to remember these long lines here and have it combined with your script. And here's also note the format of the time parameter. On top, you see here the 30 minutes where you have the hours, minutes, and seconds. And on the bottom here, you have this 3 minus 00. This would be 3 days and not 3 hours or something. So there are different time formats that you can use, and that you could confuse. So sbatch will take the parameters and your job script, and then tell the scheduler, please allocate these resources and run the commands. And then Slurm will look into the schedule, decide when it should be executed. And then we can use the sq command to look at your jobs. So you see only your jobs, and you will get this list, this table, and you will see the job ID. Every job that is allocated gets a job ID, even if it's not running yet. And you see the partition, you see the name of the job, the user, and the state. And in this case, we have 3 PD. PD means pending jobs, so they are not started yet. And we see 2 running jobs, they are already running. And then you see the time that they also already ran, the wall time, and how many nodes and which nodes they are running on. So this gives you a nice overview over what is happening right now. Then you maybe want to cancel a job because you figured out there's a mistake in my code, so I don't need it anymore. And you can use the job ID to cancel it, or your job name, the user, and so on. And you can even modify a pending job. So if it's not started yet, then you can modify some parameters. You can say, okay, I changed my mind. It should go to a different partition, or there should be a different time limit. So you say, yes?
Do the run that we can update the partition and change the time of the job?
No, it's when it's pending, if it's not running yet. So here is a nice cheat sheet with the most common parameters and some of the details of the system and some of these commands.
How many like nodes and how many GPUs are kind of free in the whole system to grab this to the top?
Yes, we also have a command for that. Yes, I was thinking if it's still coming in the slides. Okay, maybe then it won't appear in the slides.
Yeah, that's the
Yes. But okay, there was some time limit. Wanted to switch into the terminal really fluently and so on, and then it just ran out of the time limit. So in this case, in the background, we can also see that this Jupyter notebook is also running as a compute job. It's done in the background of the JupyterHub. And we see that we are here on the N2CN0309 node, as we also see here. We can do as info, and then there's some. Yes, so here with the as info command, we see the state of all of the nodes. So some are reserved or draining because there's maybe some problem with the node that has to be fixed, maybe a hardware problem. So they are taken out of the scheduling, so they can be repaired. And then we see some idle nodes and some mixed nodes where there are multiple jobs on it. And we also have a script as cluster that gives us a tabular version. So we see we have 990 nodes in total in the normal partition, and then some are unused, some are idle, some are reserved, and so on. So these partitions are disjunct, and in the normal large mem and huge mem partition, there are only CPU nodes. And in the GPU partition, there are the GPU nodes. And we also have a DGX, one DGX node for the development. Well, that's the question. So what will you do with the information?
Is that like putting my dispatch for HGP, let's say I have 1 day, and if I see that I have only like I have 8 more, I can chop with only 1 GPU available, then I put 1 GPU like I don't know 8, right?
Well, this is the difference of having the hardware under your desk, where you always have it available. It's only exclusively for you. And if you're not using it on the weekend or so, it's idling and wasting space. And on the HPC cluster, it's a shared system. A lot of people are using it. And if you have a computational job and it can't run at the moment, then it will run at a later point. So it's optimized for throughput of the computations. And this is a somewhat different way of working. So you specify what you want to be computed, and then it will be computed at some point. So interactive usage is possible, but then it always depends. So it's not not really, it's you can't really give a guarantee that you will always have this interactive usage possible. And but on the other side, if you need 20 nodes, then they will be executed at some point. And you just can't somewhere get 20 server nodes under your desk at a certain time. It's more complicated. And then it's all in all, you could also argue it's more efficient because if you're not using the cluster, someone else will use the cluster, and it's like a shared investment and shared usage of the resources. So you can also use the so with the job script thing, this is non-interactive usage. You specify what should be done, but at some point it will be executed, and then you will get the result. You can also do interactive usage. You say how much resource you need, the time, and so on, and then you say srun, and then you will get a shell. But there's no guarantee that you will get it immediately or in 5 minutes or in 5 hours, depending on how much free resources there are on the cluster. Therefore, this is then the question, what do you do with the information of the free GPUs? Will you wait until they are available, until you use them? Or will you specify your job that is most efficient with 4 GPUs and then give it to the scheduler, and then it will be executed at some point? Well, yeah, this can also happen. So we have the normal GPU partition that adhere to the normal things, but we also have the DJX with 8 GPUs, where the idea is more of a development axis where the allocations are also very limited in time. So there's a higher chance that you can get a support to do some interactive work. Okay. Um, talking about GPUs, if you want to use GPUs, then you have to specify the GPU partition and this GRES thing with how many GPUs you want to allocate. Another important thing is environment modules. This is how you specify what kind of software you want to use in your on the cluster in your job script. So every user could just compile their software themselves, but this would kind of be quite inefficient, cumbersome. You need to figure out the right parameters. So and then the question is where you would install it in your home folder, and then every user would basically compile all of the popular software themselves. So on clusters, the administrator takes care of the most software you ask them, and then they will install the software for you, and then it's also available to other people. And they can also make sure that the right parameters for compilation are used, so it's optimized for the specific cluster hardware. Exactly, and then the question is, if you have thousands of modules, of software modules, how do you access them? The answer is they are installed into a specific folder. And with the LMOD module system, you can ask to add some paths to your environment variables. This means to the path and to the LD library path, variables, and so on. So your shell can find the software that you need. So we're using this LMOD system, and this is an example of a module specification. So in this case, if you type module show and then specific module version, then it will show you what is happening if you load the module, and you see it basically just adds a lot of paths into your shell environment, and then your shell finds the software. Therefore, you before the command, you could not, before the load command, before you're loading the module, your shell couldn't find Julia, and then after the loading of the module, it can find the Julia command and can execute it. And Julia will find all of the files via the environment variables that are then defined by the module. And you can look at the available modules with the module AV command. And in our cluster, we also have this hierarchy. So they are a little bit structured or hidden behind these groups of modules. So you can add a specific complete name of the module, or you can add the group and then only the name the module. For example, you can say module load lang, and then it will open up and make available this lang group of modules. And then you can say module load Julia HPC, and then it will load the specific Julia HPC version and all of the dependent modules. With module list, you can see what modules were loaded, and it's working as a stack because the order that is used for changing your environment is important for the paths. And if you don't want the module anymore, you can use unload for a specific module, or you can use purge or module reset to reset your environment. And we also have nice script find module that where you can easily search the modules. I can also so module list. You see we only have these 3 default modules loaded. And then I can use find module, for example, Julia. And then we have this list of Julia modules found. And then I can simply, so if I'm now typing Julia, it can't find the Julia binary. It only sees the folder. And if I load, in this case, via the long name, I can also use lang and then Julia HPC. Now I'm using this very specific path. I can load it And now if I'm using module list, we see that it is loaded, and it now also finds the Julia binary to be used. And how to use it in a job script. At the top of the job script, it's a good idea to reset your module environment with module reset. And then you can specify the software that you need, the modules that should be loaded, and then you can use the or execute the software. For the JupyterHub, it also so we have this hierarchy, and usually if you just say module load Julia HPC, it wouldn't find it because they are hidden behind these categories. So you first have to do module load lang, and then you can do module load Julia HPC, and then it will find the module. Or you can use the complete name. This is the alternative. And in the JupyterHub, it also you can use modules, and then they are used for the kernels. So before the kernel started, the module is prepared in the module list in the environment, and then your kernel is started with this with these modules loaded, and you will also get new kernels. There are some Julia and Python kernels that are made available to you this way. No, so the module system is just from the cluster administrator, and the module system is also just a way to, if it's already installed in a folder, to make it available to your shell. And in our case, in our system, we are using a build system called EasyBuild, which is a build system specifically for HPC systems, where there are also like a package system with recipes, and then it generates and compiles and installs the software in the folder and generates these module files that you can use then to get access to the installed software. Exactly. Sometimes PowerPoint doesn't like me. We can take a look into an example. So here we have some files. Maybe I open them here through the So here we have some Julia code. We have just a normal script. We are loading some packages, having a main function, and then running the main function, computing matrix multiplication. And then we have our job script, and it says it's a matrix multiplication test on the normal partition. At most, it should take 5 minutes. We want to allocate 16 cores and 10 gigabytes of memory. And then we load the module that we want and run the Julia. So we also need this ---- project, so it will find the correct manifest file. I think in this example, these are old files, and I renamed them so it uses the files on the upper level. But we can, I'm here in the folder, and I can simply do as batch, and we see that it's running. So in our course here, we have made some reservations for some compute nodes, so they will be executed immediately for your accounts. And this is why it's starting immediately. So we see that it was running for some seconds and now it's gone. It's only our JupyterHub compute node running. And now if I'm looking at the files, there's a new out file. And I can take a look at the content. So we see here some information about the allocation. I wanted 16 cores, and it tells me on what compute node which 16 cores were allocated. Then there's some message about from the module system, and then the output of our Julia script. So we've discussed some different workflows that you can use with Julia and the usual workflow on HPC systems in a non-interactive way. How the jobs are scheduled on the HPC system and how to load the environment modules, how to specify your job script to let it run on the cluster. So do you have maybe some questions at this point before we go into the break? It might matter to you. So if it's if the desired version is not installed, then you can ask an administrator to install it. So it also depends on what kind of project you are using. If, for example, it can be that newer versions of packages are not working with older versions of Julia, this can happen. Then you basically, if you want to reproduce some result, you need an older version, and then you need a specific Julia version, a specific combination of Julia packages, a specific version combination, and then it does matter. Else, usually or often new Julia versions come with bug fixes and performance improvements. So you can test if it works for you and if the software that you wrote or the packages that you're using are working with the specific Julia version.